Hi, my name is Saket Kenjale, and in today's video we're going to be covering section 1.5, exponential and logarithmic functions. So in today's video we will use the properties of functions to solve equations involving exponential or logarithmic terms. We will then study the meaning and the importance of the number e, and lastly we will define hyperbolic and inverse hyperbolic functions. So now let's start with exponential functions. A common application of exponential functions is population growth. And to understand population growth, we will go through an example problem. So it says that a population starts with P0 individuals and is grown at an annual rate of 2%. So let's stop there. Just with that information, we get two pieces of information. The population starts with P0 individuals, so that means that is the original number of people. And then after that, every year it is grown at an annual rate of 2%. So this is how we would format it with this given information. So we say P1, and 1 stands for how many years there's been. So P1 is equal to P0, which is the original number of people, plus P0 times 0.02, which is the annual rate in a decimal form. And that is equal to, when we factor out the P0, it is equal to P0 times 1 plus 0.02, which is simply P0 times 1.02. After 2 years, it will become P2 is equal to P1 plus 0.02 times P1, and then we could factor out the P1 and we'll get P1 times 1.02. And as we found out earlier, we found that P1 was equal to P0 times 1.02. So when we substitute that in for over here, then we get P0 times 1.02 times another 1.02, and then we get everything is equal to be P0 times 1.02 squared. So if you see, there's a recurring pattern going on where you keep multiplying a 1.02 to each year. So from P1 there's 1.02, and in P2 there's 2. So the general population formula will be PT, where t is the amount of time in years, is equal to P0 times 1.02 to the power of t, where t is still the amount of time in years. And this formula right over here is an exponential function because of the fact that the original exponential function, or the parent function of exponential functions, is known to be this. F of x is equal to b to the power of x, where b is greater than 0 and b is not equal to 1, and b is known as a base, which is a constant like 1, 2, 3, or 4, and x is an exponent, which is always changing. And a quick note over here, it says for a function like f of x is equal to x to the power of b, where the power is the constant and the base is the element that is changing. So for a function like this, where b and x are switched, this is not an exponential function, and instead it is a power function. So quick example, this is x to the power of 6, which is a power function, and 6 to the power of x, that would be an exponential function. Now let's take a look at power functions and exponential functions side by side, and let's compare and contrast them. So we have the scale x, so it goes from -3 all the way to 6 in increments of 1, and then here we have x squared, which is a power function, and it is commonly known as being a quadratic function, which goes like that. So x squared is a power function, which is a quadratic, and then we have an exponential function 2 to the power of x, where the base is the constant and the power is the changing variable. So looking at it right over here, we could see that at x, when x is equal to 3, then the power function is equal to 9, and the exponential function is equal to a fraction 1/8. As we can see, when we go up the scale, the power function behaves like a regular quadratic. It mirrors both sides. When it's -2, it's 4. When it's 2, it's also 4. And it just keeps going on and on till we get to 36, because 6 squared is 36. For the exponential function, you can see that it starts as a small fraction getting really close to 0 at x is equal to -3, and when it climbs up the scale, it increases in value, and it just keeps getting exponentially larger until it reaches 64, because 2 to the power 6 is equal to 64. And now we have a graphical representation of these two functions side by side, and we can see, yes, the power function is our quadratic, which it has the similar shape that I showed over here. And as you can see with the exponential function, it is not really close to a quadratic, but it starts off really close to 0, and then it just bursts up, and it has an even steeper slope than the quadratic function. Now let's take a look at evaluating exponential functions. And specifically, let's take a look at the properties of exponents. So if we see on this first one, it says if x is a positive integer, then f of x will grow. And remember that in our definition for what b is, for what our base is, b has to be greater than 0, and it can be equal to 1. So if b was equal to 1, then it would just be 1 to the power of a number which is always 1, so that wouldn't work. And if it's less than 0, then if b was less than 0, then the number would keep decreasing. But because it's greater than 0, when you multiply b with x amount of factors, then it will increase. If x is a negative number, or a negative integer, then f of x will be 1 over b to the power of x, where this x is a positive integer and this x would be -1. It's just the opposite. And if x is a rational number, then x is equal to p over q, where p and q are integers. So if x was equal to p over q, like right here, so b to the power of x is the same thing as b to the power of p divided by q, and then the top integer, which is p, becomes exponent, and the bottom one q becomes a radical. Now let's take a look at this example problem. It says, suppose a particular population of bacteria is known to double in size every 4 hours. If a culture starts with 1,000 bacteria, then the number of bacteria after 4 hours is n of 4, which is equal to 10,000 times 2. The number of bacteria after 8 hours is n of 8, is equal to n of 4 times 2, which is equal to 1,000 times 2 squared. In general, the number of bacteria after 4m hours is equal to 1,000 times 2 to the power of m. Letting t equal to 4m, we see that the number of bacteria after t hours is n of t is equal to 1,000 times 2 to the power of t over 4. Find the number of bacteria after 6, 10, and 24 hours. So they gave us a lot of information right there, but the simple thing, or what we had to understand, was that this is the equation for the bacteria spread. This is how quickly it spreads. And we need to calculate the number of bacteria after 6, 10, and 24 hours. So we just have to find n of 6, n of 10, and n of 24. So let's do that right now. So if we plug in n of 6, it is going to be equal to 1,000 times 2 to the power of 6 over 4, which is equal to 1,000 times 2 to the power of, we can simplify this to 3 over 2. So if we take 2 to the power of 3 and take the square root of 2, so it will become 1000 root 8. So that's the number of bacteria after 6 hours. After 10 hours, which is n of 10, then it becomes 1000 times 2 to the power of 10 over 4, which is equal to, this cancels out, this becomes 2, and this becomes 5. So this is equal to 1000 root 32. And lastly, we got n to the power of 24, which is 1000 times 2 to the power of 24 over 2. 24 over 4. And that's just 6. So this becomes 6 is equal to 64 times 1000. And that's just 64,000. So that's the solution to this problem. Now let's take a look at graphing exponential functions. So over here it says the domain for f of x is equal to b to the power of x is all real numbers, or negative infinity to infinity, and the range goes from 0 to infinity. And over here it says that if b is greater than 1, then b to the power of x is increasing on the interval of negative infinity to infinity. And we could also write it as this. So as b to the power of x approaches infinity, so as it goes up to infinity, then x approaches infinity, so x approaches infinity here. So, and also as b to the power of x approaches 0, so when it gets really close to the x-axis, then x approaches negative infinity. And that is true. So when we go all the way to the left, then it's approaching 0. And for this one, it says if b is in between 0 and 1, then b to the power of x is decreasing on negative infinity to infinity. So it says as b to the power of x is greater than 0, as b to the power of x approaches 0, then x approaches infinity, and as b of x and b to the power of x approaches infinity, x approaches negative infinity. So basically, in short, what these two are trying to say is that the graph of this one looks something like this, and the graph of this one looks something like this. They're kind of inversed. So now let's take a look at this representation over here. And we'll also look at the rules of exponents. So as we can see in this graph, this one right over here is 2 to the power of x. As we can see over here, this one is 4 to the power of x, and it's much steeper than the previous one. And then if we look at the other side, where we have b values, which are in between 0 and 1, it has the same shape that I described over here. So it goes from being very steep to approaching 0. So this one was for b equal to 1/2, and this one is for b equal to 1/4. It's much steeper initially, and then it goes down back to 0. And what all of these have in common is that it intersects the point 0, 1. So now let's take a look at the rules, or the laws of exponents. So all these rules are really important to know. And the first rule is that if you multiply b to the power of x times b to the power of y, it's the same thing as b to the power of x plus y. So for example, if we did 3 to the power of 1 times 3 to the power of 2, it would equal 3 to the power of 1 plus 2, or 3 to the power of 3, which is 27. And also, if we were to do this without this rule, it would just be 3 times 3 squared is 9, so that's also equal to 27. So it's just a handy way to solve it quicker. And then we have the second one. So b to the power of x divided by b to the power of y is the same thing as b to the power of x minus y. So again, for an example, we have 3 to the power of 3 over here divided by 3 to the power of 1. And that should be the same thing as 3 to the power of 3 minus 1, or 3 to the power of 2, which is 9. And we could do the same thing over here. If we do it for real, then it would be 27 divided by 3, which is just 9. The third rule is this. So if b to the power of x is all multiplied by y, then we could just multiply the exponents. Next, for rule number 4, if a times b is all multiplied by x, then we could distribute the exponent and give 1 to each of the numbers inside of the parentheses. So it just distributes and it ends up being like that. So lastly, for number 5 is if a to the power of x is divided by b to the power of x, it's the same thing as a divided by b all to the power of x. Now let's practice using the laws of exponents with an example problem. So this one says, use the laws of exponents to simplify each of the following expressions. So let's start with part A. So we notice that this 2 is being multiplied by this x to the power of 2 over 3, and everything is being multiplied by 3. So using the fourth law, this one right here, we can distribute the 3 to both the 2 and the x to the power of 2 over 3. So if we do that, we would get 2 to the power of 3 times x to the power of 2 over 3 times 3. And these two will cancel out, so we'll be left with 2 to the power of 3 is equal to 8, and then we're multiplying that by x to the power of 2. Looking at the denominator, we could do the same exact thing. We could distribute the 2 to the 4 and to the x to the power of negative 1/3. So it will become 4 to the power of 2 times x to the power of negative 1/3 times 2. And that will just simplify to negative 2 over 3. Then the 4 to the power of 2 would just become 16. And then we could cancel this out because 8 times 1 is equal to 8, and 8 times 2 is equal to 2 is equal to 16, sorry. So now, finally, we could use the second rule and simplify it to its furthest, because we have an x squared on the numerator and an x to the power of negative 2 over 3 in the denominator. So we could subtract the 2. So it would become x squared minus negative 2 over 3. And 2 is just the same thing as 6 over 3. So then it would just become x to the power of 6 over 3 plus 2 over 3. And that's just equal to 8 over 3. So our final answer would be x to the power of 8 over 3 all over 2. So that was part A. Now let's look at part B. So part B reads x cubed times y to the power of negative 1 all to the power of 2 all over x times y to the power of 2 all to the power of negative 2. So again, let's distribute the 2 in the numerator. So that would become x to the power of 3 times 2, which is 6, and times y to the power of negative 1 times 2, which is negative 2. Then we could do the same thing in the denominator. We could distribute the negative 2 to the x, so it would become x to the power of negative 2 times y to the power of negative 4, because 2 times negative 2 is equal to negative 4. Then we can see that we can use the second rule again to simplify this expression to the furthest. So using the same logic that we did over here, we can do x to the power of 6 minus negative 2, which will then become x to the power of 8. And then for the y's, it will become y to the power of negative 2 minus negative 4. And that is just equal to y to the power of 2. So our final answer will be x to the power of 8 times y to the power of 2. And that now completes this problem. Now let's take a look at the number e. So there are special types of exponential functions that occur in real-world applications. And to look into it further, we're going to go through an example problem. So the problem reads, suppose a person invests P dollars in a savings account with an annual interest rate R. An annual interest rate R compounded annually. So again, P is amount of dollars, so we could give it an imaginary value, which is $1,000. So there's P dollars in a savings account. There's $1,000 in a savings account with an annual interest rate R. So usually the interest rate is in a percentage, but in this case, it is already converted into a decimal point. So let's assume that R right now is a decimal. So the amount of money after 1 year is, so this is the function a of t, where t is the amount of time in years. So a of 1, so after 1 year, that would be equal to p plus p times the interest rate, which is r, and then simplified, or when you factor out the p, you get p times 1 plus r. We did a very similar thing in the beginning of the video, right over here. It's the same process over here. So now going back. Now after 2 years, it is going to be a of 2, so 2 years is equal to a1 plus r times a1, which is equal to, it's because we found that a1 is equal to p of 1 plus r, so it's equal to p of 1 plus r times r of p times 1 plus r, which is equal to p of 1 plus r squared. So the general equation for this scenario is a of t is equal to p times 1 plus r to the power of t, where t is the amount of time in years. If the money is compounded 2 times a year, then the amount of money after half a year is going to be r divided by 2. So if it's compounded 2 times a year, then if r would be r divided by 2 basically. So now if we continue with the process, it's going to be a of 1/2 is equal to p plus r divided by 2 times p, which is equal to p times 1 plus r divided by 2. After 1 year, it would become a1 is equal to a of 1/2 plus r divided by 2 times a of 1/2. And if you simplify it down, then we get p times 1 plus r divided by 2 squared. So it's just, again, it's the same process that we did over here. So now after t years, the amount of money in the account is A of t is equal to p times 1 plus r divided by 2 times 2t. Because of the fact that it's compounded 2 times a year, that is why there is r divided by 2 and 2t. So the general equation of this situation is A of t is equal to p times 1 plus r divided by n times to the power of n times t. So in this case, n is the amount of times that the money is compounded per year, and t is the number of years, like I said earlier. Now, what happens as n approaches infinity? So for now, we are going to substitute n over r. We're going to substitute n over r for m. And so when we put it into this equation right over here, because it has r over n, then that means that r over n is equal to 1 over m, because it is the reciprocal of this, because n over r would just equal to m. So when we go through with it, then we would get 1 plus 1 over m. And then here, with the original equation being to the power of n times t, we're going to have n equal to m times r. So the final equation that we're going to get now is 1 plus 1 over m to the power of mrt. So this is the equation where we can examine the behavior of 1 plus 1 over m to the power of m as m approaches infinity, and we have to see if there is a trend. So this is the variable and this is the function, and as we approach infinity, we're getting to a very high value. We can see that we are approaching a number between 2.7 and 2.8. So as m approaches infinity, it approaches a number between 2.7 and 2.8, and that number is called e. So e is approximately 2.718282. And so we can conclude that if a person puts p dollars in an account at an annual interest rate compounded continuously, compounded infinitely, then A of t is going to be equal to pe to the power of rt, since e is this expression that we got over here. So we just substituted for that, and because it goes to infinity, it is known as this value over here. So this is our main equation that we use for annual interest rates, or compounded for interest rates that are being compounded continuously. And so the function f of x to the power of f of x is equal to e to the power of x. This function right over here, it's called the natural exponential function. And since e is greater than 1, because e is equal to 2.7 something, e to the power of x is increasing on negative infinity to infinity. And a cool thing about this function e to the power of x, that as we approach the y-axis, this slope over here, this like curve over here, at the y-intercept, if you take the tangent line of the function, and by the way, a tangent line is just a line that you take between one point and it only intersects one point. So the specific definition, it says a line that passes through point a comma f of a. So in this case it would be 0 comma f of 0, and at e to the power of 0 is just 1, so that's why the it crosses through 1. So it passes through that point and it has the same slope as f at that point. So right over here, it would have the same slope. So it has a slope of 1, and that's pretty interesting. Before we get into this example problem, I just wanted to say that if everything before that was confusing to you, then don't worry. It's not needed to know. It was just an explanation or a proof of how E came to exist. But what you do need to know is how to use E in the equation A of t is equal to PE to the power of RT. So you do need to know how E is used to compound continuously, basically. So now let's take a look at example 1.35, compounding interest. So it says, suppose $500 is invested in an account at an annual interest rate of R being equal to 5.5% compounded continuously. So when it says compounded continuously, that is the key to realizing that this equation, A of t is equal to PE to the power of RT, is going to be in use in this problem. So now let's read A. It says, let T denote the number of years, so T denotes the number of years after the initial investment, and A of T denote the amount of money into the account at time T. So find the formula for A of T. So let's do that right now. So for A, they want us to find a formula for A of T. So obviously we'll have A of T is equal to P. So what's P in this situation? P is the original investment of $500. So P is going to be equal to 500. Then we're going to have E to the power of R, and R in this case is 5.5%, and to put that into decimal notation, it will be 0.055 T. So this is our answer for part A. They just wanted to know the equation. So for part B, now it says, find the amount of money in the account after 10 years and after 20 years. So basically what they want us to find is A of 10, and they want us to find A of 20. So let's first solve for A of 10. So right here, we just substitute that. It will be equal to 500 E to the power of 0.055 times 10. And then let me use a calculator. So when I plug it in, it's going to be 500 times E to the power of 0.055 times 10. So I got 866.6265,089. So if we simplify that out, that'll be roughly $866.63. So that's the amount after 10 years. After 20 years, it's going to be 500 E to the power of 0.055 times 20 now. So that is going to be equal to, putting on the calculator, is going to be equal to $1,502.08. So that is our answer for A of 20. And we now completed this problem. Now let's have a look at logarithmic functions. So logarithmic functions are the inverses of exponential functions. And since exponential functions have the parent function of f of x is equal to b to the power of x, and have a domain of negative infinity to infinity and a range of 0 to infinity, its inverse, which is logarithmic functions, has a domain of 0 to infinity and a range of negative infinity to infinity. So its domain and range were flipped. So this is the general equation for a logarithmic function. It's log base b of x is equal to y. And that only works if b to the power of y is equal to x, where b is greater than 0 and not equal to 1, the same conditions in that were used in exponential functions. So here is an example. So right here, this is an exponential form, and it has 2 to the power of 3, which is equal to 8. And using that, so b is equal to 2, y is 3, and x is 8. So if we were to use that in this form, in logarithmic form, since we discovered b to be 2, we'll have log base 2 of 8, because 8 is equal to x, and that is equal to 3. So the 3 over here becomes the 3 over there, and is equal to y. So log base 2 of 8 is equal to 3. So what I do to remember this is that I have this pattern where b is 1, x is 2, and y is 3. And then for this one, for the exponential form, it's going to be 1, 3, 2. So the log is going to be 1, 2, 3, and the order for the exponential function is going to be 1, 3, 2. So that's how I remember it. So basically, we have 2 to the power of 3 is going to be equal to 8, and 2 to the power of 3 is equal to 8. And if we want the logarithmic function based off of the exponential function, we'll have log 2 base 8, log base 2 of 8 is going to be equal to 3. So that's just the way I remember it. I'm not sure if that helped you, but hopefully it did. Alright, now we have another example. So we have log base 10 of 1 over 100 is going to be equal to negative 2. And that works since 10 to the power of negative 2 is 1 over 100. And lastly, we have log base b of 1 is equal to 0, and b can be any number, any real number in this situation, because if we look at its exponential form, it becomes b to the power of 0, and anything to the power of 0 is just 1. And by the way, when I said any real number, it meant any real number above 1. And so since y is equal to log base b of x, and y is equal to b to the power of x, and they are inverse functions, so we could use this rule that we learned in 1.4, which was inverse functions. So if we take f of g of x, and f and g are both inverse of each other, we should get x. And also, if we take g of f of x, then we should also get x. So it works the same with these two functions because of the fact that they are inverses. So if we take log base b of b to the power of x, then these two right over here, they cancel out, and we're just left with x. And same thing for b to the power of log base b of x. These two will cancel out, and then we're going to be left with x again. So the most common log function is one with a base e that we learned about earlier. And so we have a log base e instead of an integer value. It's just going to be log base e of x, and we have a specific notation for that. It's called ln of x, or natural log. It's called the natural log. So for an example, if we take the natural log of e to the power of x, that's going to be equal to x because it's the inverse. So if we if we substitute e for b in the situation, like up here, then it still works the same. And it's the same logic for over here. An important thing to know is that ln of 1 is equal to 0. And so since f of x is equal to e to the power of x, and g of x is equal to ln of x are inverses, So we have the same logic that I explained earlier with these two. So this is the graph of e to the power of x that I showed you before, and this is the graph. This right over here is the graph of ln of x, and you could clearly see based off of their graphs that they are inverses because they reflect over the line of y is equal to x. And this is an example of different log functions. So the orange one is the parent function of ln of x, and this one right over here is log base 2 of x. So it starts a little steeper, or starts a little farther away from the y-intercept, and then it goes out, and then we have y is equal to log base 10 of x, which is in this teal color or this blue-green color, and it is very close to the y-intercept, and it kind of flattens out like really quickly compared to the ln of x and the log base 2 of x. So now we're going to take a look at the properties of logarithms. So in this case over here, it says if a, b, and c are greater than 0 and b is equal to 1, and r is any real number, then these rules apply. So it says, the first one says log of base b of a times c, so log base b of a times c is equal to log base b of a plus log base b of c. And then the next one is log base b of a divided by c, that is going to be equal to log base b of a minus log base b of c. And the last rule is when you have a log base b of a to the power of something, and the something is any real number, then we could take this r and we could put it in the front right over here. So we're going to have r log base b. So it's r times log base b of a. So now let's solve this example problem 1.36. It says to solve each of the following equations for x. So let's take a look at example A. It says that 5 to the power of x is equal to 2. So how are we going to solve for x when x is a power? So a simple way to do that is to convert this exponential form into a logarithmic form. So like I showed you guys earlier, right over here, this is the form, the b to the power of y is equal to x is the exponential form, and this log base b of x is equal to y is the logarithmic form. So with the steps I showed you before, if the logarithmic form has the order of 1, 2, 3, then this will have the order of 1, 3, 2. So looking back at our problem, the 5 is 1, the x is 3, and then the 2 is going to be 2. So this is a 1, 3, 2 pattern, and if we want to convert it into logarithmic form, it's going to be log base 1, so 1 is 5 in this case, the 5 is the b, and then the 2 is going to be in the parentheses, and that is step 2. This is the step 2, and x is going to be 3. X is going to be our last value. So now we could solve for x. It is actually solving for x. So x is equal to log base 5 of 2, but we can get it down to a decimal answer using our calculator. And so how we want to solve for that using our calculator is that when you punch in log on your calculator, it's only going to show you log, and it's going to give you parentheses. So what you want to do is you want to take log of 2 and you want to divide it by log of 5, and that will get you your decimal answer. So if I do that on my calculator, I'm going to put log of 2 divided by log of 5, click enter, and I get my x is going to be equal to 0.4306, or x is going to be equal to 0.431. So that's our answer for part A. So now let's move on to part B. So just a warning, part B is quite a difficult problem and involves some unique steps that you have to take in order to solve for the x's, but hopefully my teaching will be able to suffice, and hopefully you'll understand how to solve this problem or any problems like this. So let's move on to B. It says e to the power of x plus 6 times e to the power of negative x. That's going to be all equal to 5. And we want to solve for x again. So what we have to do in the beginning is that we have to multiply the whole equation by e to the power of x. And this will soon make sense later. So if you're confused right now, hopefully it will make sense later. So if we multiply everything by e to the power of x, we will get e to the power of x times e to the power of x plus 6 e to the power of negative x times e to the power of x. That's going to be equal to 5 times e to the power of x. And now, because of our exponential rules that we looked at earlier, and I'll show you them right now, because of this, rule number 1, if you multiply two values with the same base and different, or it could be the same exponent, then you could just add the exponents together. And that is our case in this problem. So if we go back, if we see we have the same base e for both right over here and right over here. So we could just add the exponents. So it's going to be e to the power of x plus x, or that's going to be 2x. And we add that, it's going to be e to the power of negative x plus x, which is just 6e to the power of 0. And now anything to the power of 0 is just 1, so it's basically the same thing as 6, or 6 times 1. And that's all equal to our 5e to the power of x. Now what we want to do is that we want to bring the 5 to the other side, so we'll subtract by 5 times e to the power of x from both sides, and we will get e to the power of 2x minus 5 times e to the power of x plus 6. That's all equal to 0. And what we lastly have to do is that we have to use one last exponential rule that I will show you right now. It is this one. It's going to be rule number 3. So if we have b to the power of x all to the power of y, it's the same thing as b to the power of x times y. But what we have right now is we have e to the power of 2x. And so the 2 and the x are multiplying together. And so what we can do is that we can take e to the power of x, and we could multiply, and we could take the power of 2 to the whole, to this total e to the power of x. And if we reverse it again, we will get our e to the power of 2x. So we could do it like this. We could write e to the power of 2x as e to the power of x to the power of 2. So now going back to our problem, right here, we could write this e to the power of 2x as e to the power of x to the power of 2 minus 5 e to the power of x plus 6 is equal to 0. And now here's the important part. So I separated the x and the 2 for a reason. So after the separation, we can see that this looks sort of like a quadratic function. And that's because it pretty much is a quadratic function, but the only difference is that instead of x, we have e to the power of x. We have these e to the power of x's over here. So what we want to do is we want to set x, let me do that in a different color. We want to set x equal to e to the power of x. So this change formula is going to be x squared minus 5x plus 6. That is going to be equal to 0. And now we could easily solve or factor this quadratic, and we are going to get x minus 3 times x minus 2. That's going to be equal to 0. And so now we could change back these x's into our e to the power of x over here. So let's do that. So this can become e to the power of x, and this can become e to the power of x as well. And now we have two different equations. We have e to the power of x. We could have two different equations. We have e to the power of x minus 3 is equal to 0, and we have e to the power of x minus 2 is equal to 0. So let's first work on this e to the power of x minus 3 is equal to 0. We can add 3 to both sides, and it'll become e to the power of x is equal to 3. And now this is in exponential form, but we could turn it back into logarithmic form by using the 1, 2, 3, and the 1, 3, 2 rule. So this is 1, 3, 2. So that means it will become log base e of 3 is equal to x. And then if we can simplify that out, because log base e is just natural log. So it will just be natural log of 3 is equal to x. So this is one of our solutions. And now let's do the same thing for e to the power of x minus 2 is equal to 0. So we found one. Let's solve for the other. That's a dark color. I'm not going to use that. So we add 2 to both sides. It's going to become e to the power of x is equal to 2. And so we could use the same logic, and that will end up being natural log of 2 is equal to x. So this is our second solution, and so that now completes this problem. We have natural log of 2 is equal to x, and natural log of 3 is going to be equal to x as well. Now let's work on example problem 1.37. It says to solve each of the following equations for x. And so, it was the same prompt for 1.36, for question 1.36, but this time we have to take a little different approach. So before we were using the logarithmic form, and b was a really hard problem, so let's not worry about that. But this time for all a, b, and c, we have to use one of our properties that we learned right over here. So let's do that right now. So I'm going to write a over here, and I'm just going to rewrite the question. So a says ln of 1 over x is equal to 4. And so what we could do is that using our second rule, using the quotient rule of our logarithmic functions, since log base b of a divided by c is just log base b of a minus log base b of c, we can do the same thing with our problem over here. So this will become natural log of 1 minus natural log of x. That is going to be equal to 4. And remember the note I talked about earlier? That important note. Natural log of 1 is always equal to 0. And we have a natural log of 1 right over here. So this is just equal to 0. And we have negative natural log of x is equal to 4. Now we could move the negative sign to the other side. We will get natural log of x is equal to negative 4. And finally, we can take e to the power of natural log of x, and we could take e to the power of -4. And we could do that because they are inverse functions, so they will cancel out. So we were going to be left with x. We're going to be left with x is equal to e to the power of -4. And that's our answer, but we could simplify it down to x equals to 1 over e to the power of 4, just to keep the exponent positive. Now moving on to b, I'll do it right over here. So b says log base 10 of the square root of x plus log base 10 of x is equal to 2. So the best way to approach this problem is to combine these two terms, and then we will find a way to simplify it. So let's work on it right now. So we have log base 10 of, and using one of our properties, which is the first property, we could combine them two together, and they will be multiplying each other inside of the parentheses. So going back, it will be the square root of x times x. This is all in brackets, and that's all equal to 2. So what we could do now is that we can multiply these two together, and we could use an exponential rule. So knowing that the square root of x is the same thing as x to the power of 1/2, we could just then add the x's together because they are the same base. And this is x to the power of 1. So if we do that, we will get log base 10 of x to the power of 3/2. So we'll have that's going to be equal to 2. Using another one of our logarithmic rules, we can take the exponent r and put it out at the front. So we could do that with our 3/2. So doing that, we will get 3/2 log base 10 of x is equal to 2. Then we could multiply both sides by 2 over 3. These will cancel out. 2 over 3. And we will get log base 10 of x is equal to 4 over 3. Now we could turn this into an exponential function. So this is a logarithmic function, which is 1, 2, 3. And an exponential function would be 1. So the 1 is the 10. This is 1. And so it will be 10 to the power of 3. So the 3 is the 4/3. That's going to be equal to x. So if we put that into our calculator, we will get x. So let me do that right now. It's 10 to the power of 4 divided by 3. And that's equal to roughly 21.54. So that's our answer for part B. Now I do not have enough space for part C, so I would just delete A. Okay, now let's work on C. So C says the natural log of 2x minus 3 times the natural log of x squared is equal to 0. So one thing that I noticed immediately is that there's this 3 just hanging out over here, and that could be put into the parentheses because of our because of the log property, which is the third one. So let's just do that right now. So it's going to be natural log of 2x minus natural log of x to the power of 2 times 3. That's going to be equal to 0. And so this is just equal to 6, x to the power of 6. And then we can combine these two together because of the second logarithmic property. So we could have these dividing itself into one log equation. So it'll be natural log of 2x over x to the power of 6. That is going to be equal to 0. And then we could simplify this further by canceling out one of these x's at the top, and that would just become 5. And that was another one of our exponential properties as well. So now we're left with this. And so you're probably thinking, how can I solve for x? And the answer to that is that the natural log of something is equal to 0, and that something has to be 1, because that is how natural logs work. Natural log of 1 is equal to 0. So then now we can use now we have the equation 2 over x to the power of 5 is going to be equal to 1. And now we could solve for x this way. So the first step is multiplying both sides by x to the power of 5. We're going to get 2 is equal to x to the power of 5, and x will be equal to the 5th root of 2. So that is our answer for part C. Now let's look at change of base formulas. So let's first look at this example right over here. It says let a and b both be greater than 0 and let them both not equal 1. So if that is the case, then a of x is going to be equal to b to the power of x times log base b of a. And this is the case because if we look at this, b to the power of log base b of a to the power of x, that is the same thing as b to the power of x times log base b of a. And this is one of our logarithmic rules that we discussed about earlier. We could take the exponent and we could put it in the front. And so now we could cancel this, and that will leave us with a to the power of x is equal to b to the power of x log base b of a, which is exactly what is stated right over here. And if b is equal to e, then this equation then reduces to a to the power of x is equal to e to the power of x times ln of a. The second change of base formula is this. Log base a of x is the same thing as log base b of x over log base b of a for any real number where x is greater than 0. And so if b is equal to e, this equation reduces to log base a of x is equal to ln of x divided by ln of a. And so just a reminder, b can be any real number or any real integer that is greater than 0. So now let's take a look at this example problem. It says, use a calculating utility to evaluate log base 3 of 7 with the change of base formula presented earlier. So we have log base 3 of 7, and using the second rule, this one right over here, we can change the base and it will become like this. We could say log of 7 over log of 3. And when you put it into your calculator, the calculator automatically puts the base as 10. So let's just put it as 10. When we solve with our calculator, and if I were to say log of 7 divided by log of 3, the answer is 1.771. So this is the answer for this problem. So this is going to be it for section 1.5, exponential and logarithmic functions. And before I leave, I just wanted to say that we were supposed to go through hyperbolic functions and inverse hyperbolic functions, but I felt that 1, this video was getting too long, so I wanted to cut it down. 2, I felt that the content was confusing and kind of difficult, so I decided not to include it. And 3, I felt that it wasn't really relevant to our AP Calculus AB course, so I decided that it wasn't a good idea to add it in. So this is now the end of our pre-calculus journey, and I will see you in Unit 2, where we are going to start with limits. See you then.